Hello everyone, today we are demonstrating our signal network and system mini project. I am Saniya along with my teammates Piyush and Samar. We have prepared this project under the guidance of Professor Najib Gatte and Professor Shanti Swami. Welcome to this video on live audio noise cancellation using LMS adaptive filtering in MATLAB. In this project, we will explore how to reduce background noise from recorded audio, allowing speech to come through loud and clear. This technique is ideal for situations where background noise interferes with speech, like in crowded places or noisy offices. We will use MATLAB to record audio and noise and apply the least mean square adaptive filtering technique. LMS adapt to different noise environment in real time, helps to reduce unwanted sounds and enhance voice clarity in this demo, we will record a sample, filter out the noise, and compare before and after audio to evaluate the noise reduction achieved. This method of noise cancellation can be highly effective in various applications, from enhancing call quality to improving audio clarity in recordings. By using adaptive filtering, we are allowing our filter to learn and adapt to the noise, making it more flexible than simple static filters. So let's dive in and see how we can implement this in MATLAB to create powerful and flexible noise cancellation system.
Hello everyone. Now I'll be taking you through the working of the live audio noise cancelling project using LMS adaptive filtering in MATLAB. Now the first step would be giving an input. So I'll run the project. Now we are recording. I'll say something. This project demonstrates a real-time audio noise cancelling system using LMS adaptive filter. It removes background noise while preserving speech clarity, making it ideal for improving voice communication. Now the recorded speech will be heard. Recording. I'll say something. This project demonstrates a real-time audio noise cancelling system using LMS adaptive filter. It removes background noise while preserving speech clarity, making it ideal for improving voice communication. Now we'll be hearing the after noise cancelled and amplified signal. Recording. I'll say something. This project demonstrates a real-time audio noise cancelling system using LMS adaptive filter. It removes background noise while preserving speech clarity, making it ideal for improving voice communication. So this is it, the working of the project. Now we'll go through the explanation of the codes.
Now we see the code explanation part. The first step is setting up parameters. First we set up basic parameters for recording and filtering process. The first one is sampling frequency. We set the sampling frequency to 44.1 kHz, a common standard for audio like in CDs. This frequency is high enough to capture human speech clearly. The next one is duration. Here we set the duration of audio recording to 15 seconds, which will give us enough time to capture background noise and speech. The next one is filter order. The adaptive filter order is set to 32. This means the filter will use 32 previous samples to adjust its coefficient, giving it enough information to adapt effectively. The last one is the step size. For LMS algorithm, controlling how quickly the filter adapts, a smaller step size means slower adaptation but may improve the stability. Next step is setting up the audio recorder. Next we set up the audio recorder to capture sound for 15 seconds. Rec object is equal to audio recorder in bracket fs, 16, 1. This line initializes the audio recorder. Fs specifies the sampling rate of 44.1 kHz. 16 sets the audio bit depth to 16 bits, which is standard for clear audio quality. 1 indicates mono recording, that is one channel. Mono is sufficient for this project as we are focusing on the voice. Then disp start speaking, that specifies displays a message prompting the user to start speaking. The next is record blocking. This line records audio for specified duration, that is 15 seconds, and blocks further code execution until recording is completed. The next line is for displaying a message indicating the end of recording. The next step is retrieving the recorded audio data. After recording, we retrieve the audio data to process it. Okay. This line retrieves the recorded audio data from the rec obj and store it in recorded underscore signal. The data includes both speech and any background noise captured during the recording.
Now for the fourth step, high pass filtering. Now we apply a high pass filter to reduce low frequency noise such as hums from machines or air conditioning. Here the HP cutoff function. It sets the cutoff frequency for the high pass filter to 300 Hz, allowing frequency above 300 Hz to pass while attenuating low frequencies, often noises. The lower function b is equals b comma a. It the butter function designs a sixth order Butterworth filter which has a smooth frequency response. The high specifies the that this is a high pass filter. The filtered signal function here specifies that the high pass filter is taken to recorded signal producing filtered signal. This filtered version of the signal has reduced low frequency noise. Now for the fifth step, plotting the filtered signal. We plot the filtered signal to visually inspect it. The figure function opens a new figure window and the plot function here plots the filtered signal over time. Now taking us to the sixth step, detecting signal silent region for noise estimation. To estimate the noise, we identify silent regions in the signal where only background noises is present. Now the threshold function, it sets the threshold for silence detection. Samples below the amplitude are considered silent or background noises. Silent amplified function finds the indices in filtered signal where the absolute amplitude is below the threshold, marking them as silent samples. Now, Estimated noises calculates the average amplitude of the silent sample to estimate the noise level in the recording.
The seventh step is initializing LMS filter parameters. Now we initialize the LMS filter which will adaptively cancel the noise. The first line is W is equal to zeros in bracket filter underscore order, comma 1. Initializes the filter coefficients as a column vector of zeros with a length equal to filter underscore order. This will update dynamically. The next line is n is equal to length in bracket filtered underscore signal stores the number of samples in filtered underscore signal for the use in a filter loop. The next line is y is equal to zeros in bracket n comma 1 initializes the output of the filter as a column vector of zeros. Then e is equal to zeros in bracket n comma 1 initializes the error signal as a column vector of zeros. The eighth step is LMS adaptive filtering loop. In this loop, we will apply LMS algorithm to adapt the filter and cancel out the noise. Here is a for loop. The loop start for n is equal to filter underscore order to n. Loops through each sample starting from filter underscore order to the end. The first line, this line extracts a segment of filtered underscore signal in reverse order, acting as a filter input. Then the next line, y of n is equal to w dash into x, computes the filter output by taking the dot product of w and x. The next line, e of n, this calculates the error signal as the difference between current sample and the filter output. And the last line for the for loop is updates the filter coefficients w based on the error step size mu and the input segment x. The ninth step is amplifying and normalizing the noise cancelled output. To improve quality, to improve clarity, we amplify and normalize the noise cancelled output. Here the amplification factor is 1.5. That's an amplification factor for the clarity. Then E is equal to E multiplied by amplification factor. We multiply E by the amplification factor. The next line, this line normalizes E to 90% of maximum amplitude to avoid the clipping. And the last step is performance evaluation. Finally, we calculate the noise reduction in decibel. This line compute the power values for the noise reduction, and nr underscore dB. This will gives the noise reduction in decibels.
Let's see real-world application of noise cancellation. Adaptive noise cancellation has many impactful applications in daily life and various industries. Here are some key examples. Smartphone. It enhances call clarity by reducing background noise, allowing clear communication even in noisy environment. Second is noise cancelling headphones. It is widely used for creating a peaceful listening experience by actively cancelling out ambient sound, ideal for travel or busy workplaces. Third is speech recognition. It improves accuracy in virtual assistant like Siri and Alexa by filtering out background noise, isolating user voice for better command recognition. Telemedicine. It ensures clear doctor patient communication in telehealth so critical medical details are not lost due to background noise. Video conferencing reduces distraction in remote work meeting by eliminating noises from pets, traffic, and other household sounds. Sixth is automotive noise reduction. In cars, adaptive noise cancellation reduces in cabin sound from engine, roads, and wind, creating a quieter and more comfortable ride. Each of these applications uses similar noise cancellation technique to what we have demonstrated, highlighting how adaptive filtering improves clarity and communication across different scenarios. Thank you.